we got going on? We actually, if we can, I'd like to almost start Lagrange today.
But he hasn't posted yet.
And go through Lagrange. I don't think we're spending that much time on Jacobian. We probably keep that course dead, right? It's done. So we will wrap that up today as well.
Yeah. The example was 512, wasn't it?
12, be 512, yeah. Yeah, we went over 513. We'll kind of do 513, 514 today. We just discussed that. Just a couple of slides. Just want to go over 514 there. If I have you for senior project, we definitely need to have a conversation this Friday. We are meeting this Friday, yes? At 4:30?
Wasn't that just for
Friday.
Wasn't that for analysts?
No, but we're meeting.
Yeah, we are meeting.
At what time, 4:30?
I thought it was 3.
No, because I'm double booked on that one now.
4:30?
Because we have, I think we're also doing NGCP, right? Maria?
Hmm?
NGCP is this Friday too, right?
Mm-hmm.
So we have to do 4:30. And we'll go over the IK code as well. Maybe you're asking about this. We'll go over that anyway. So with that stuff, if we have time, we'll jump into later on. So again, going back to where we were on the Jacobians and the velocities, again, we talked about the idea of referencing it to the end effector or the hand frame. And so to reference it to the hand frame, we did this little trick. Let's just kind of go back and talk about what we were doing. We did this trick saying we know there's going to be some matrix right here that's going to give us that relationship. We don't know exactly what's in it yet, but we know that we're going to define that. And so that's what we're going to do. So we're saying that we can compute or we can find this delta matrix operator with respect to some frame T. And again, so we said that we're going to have the dt is going to be a delta. This is to the global frame of a transform. And we said, okay, look, if we take that transform matrix, we can also find that delta operator over here as well. And so we kind of did a little trick where we said, okay, we wanted to make it look like this, but we want to solve for that. So if we take the inverse and we put it over here, we remove that t on that side, and we can solve for that delta operator with respect to that t. Again, we don't necessarily know what that's going to look like. We don't know what this is going to look like or anything like this, but we can say, okay, this is what we want it to look like. So how do we compose it? That was the idea. So we also know that this T inverse, we can take the T inverse, but we can be smarter about our T inverse. And that was the idea of this relationship right here. So this is our T inverse matrix, and this is the way we perform that P vector, that P submatrix. We dot it with the axis of interest and the destination, so we're taking the projection, and we're taking that P of that projection. So this becomes our rotation submatrix. And this becomes our displacement submatrix. So when we look at that, we said, okay, here is our rotations right here. And so this is going to be that delta dotted with N, our delta dotted with O, our delta dotted with A. And here we're going to be taking the cross product right here. So that's N dotted with the cross product of that delta to the P, and then we're going to add in that small delta T. So that was the idea there. And then we kind of said, okay, here's our cross products. We actually went through and computed what it would look like if we actually used some numbers to find this delta operator with respect to, say, for this example, frame B. Okay. Everybody with me so far? And then we continued that example where we found, so we found a cross product right here. add it in our delta D, or our delta D. And then here we find our dx, dy, dz by computing that dot product. And that generic process, so this guy right here, that delta cross P plus our D. So we take the dot product for each one. And then here we found the rotational elements so that we can construct the overall idea. Again, what we were trying to do was find the representation relative to the hand in the format that we found through the global reference frame. So then we can find this operator relative to a frame, in this case, this frame. Again, our implications we're able to relate the frame updates, right? So it's frame-to-frame relationship is really where we're going with that. And then we also reminded ourselves that the differential motion that we have right here is this portion right here. And we saw it today, right? We saw it today in the Coppelia sim, where we actually had these guys right here, right? Our velocity about x, our velocity about y, our velocity about z, our change along x, our change along y, our change along z. Because what we're really trying to do is we're trying to find what this is. What is that velocity for that motor? In other words, what is that voltage for that motor? Because this is all we can control. So when we take our controls class and we are doing PID on a velocity, that's what we're doing. And in general, we're doing the velocity control. We can do a servo control, but let me ask this question. This is a fundamental question. This is a very good question. It could show up on your exam. Do I control to theta, or should I control to theta dot?
Theta dot.
Why?
Because it's velocity.
And
that's one thing we can control.
But what if so why can't I control the theta?
But you can indirectly, but you can't directly.
Well, so let's suppose I want to have a controller that says I want to make sure I go exactly to that theta. Okay, because that's where we did our forward kinematics. We did to a theta, didn't we?
Mm-hmm.
So why do I want to control to theta? Why would I rather control the theta dot?
This doesn't control the areas you
Slot.
No. So I could do a position servo and say that, okay, move my velocity such that I can control to theta. I could do that, right? But do I want to? Do I want to make my dominant variable of control to theta or my dominant variable control to theta dot?
I don't know. The only thing that's going on in my head right now is like, you remember those encoders you were teaching us?
Mm-hmm.
So we can get position, but like it's a lot harder and it's more prone to.
Yeah, forget about the sensing method. Let's remove that. The question I'm asking is, I think, more basic and even more, I wouldn't say theoretical, but it really drives the theoretical point.
Is it because it's smoother?
No. Well, I shouldn't say it could be. Why would it be smoother?
Because you're speaking on the general motion of the joints. I don't know. I'm sorry.
Well, a lot of that thought will.
When you control the velocity, you can determine like how fast you move to that point.
Uh-huh.
So there may be some case where you need to move faster or slower, so you don't have the jerking.
So you guys are kind of dancing around it a little bit, but let's look at fundamentally what this matrix is. That's vector. Does the Jacobian relate position or velocity? Velocity. So if I have a controller set to theta, then this is still controlling to theta dot, right? Because I can only control motor velocities, like you all said. But if I have a PID that's also controlling an outer loop to theta, as well as theta dot, and I want to make theta the dominant, what do I say? This could go above and up and down, right? But if I go up and down, then that means these velocities will change. So yes, I might have gotten my theta, but I did it at sacrificing all of this. Now let's go one step further. Yay, I got theta. So I got theta 4 exactly where I want. But in the process of doing that, theta 4 dot, we kind of did up and down like this, right? And if I do that, my velocity over here is going to change, correct? And if I integrate over time, that velocity, in other words, I go from this point to this point at this velocity, is it going to be where I expect it to be? No. Because I'm going to have all these other little delta theta 4, right? So it's gonna get theta 4 to where it needs to go to. But in the process of doing that, because I have this Jacobian, it's not 100% linear relationship to this guy, because I have all these sines and cosines potentially in through the rotations. Then what's gonna happen is that's not where it's going to be, because these velocities all changed. So this is linearly changing, but this is not. So that position could be something completely different. So I can have a position error here, but I'm position correct here. But if I control my velocities, then I control my velocities. But after I've gone through all my degrees of freedom, through this Jacobian, then my differential position is where, or my final position through these differentials are where I want it. Does that make sense? Or should I say it again?
Say it again.
Theta controls the position.
As if I was a fifth grader.
Okay, so if I'm controlling position, I'm going to, if I control position and velocity, and I want position to be 100%, so I'm going to adjust my theta dots to get my theta. In the process of adjusting those theta dots, I've got ups and downs, right? I've increased and may decrease my velocities, right? To increase and decrease my velocity, I'm going to have an effect over here. But that theta, that theta right there is not a 1-to-1 of d3, for example, or dz, for example, or dy, or dx, right? All of these have contributions from all of these. It's not a 1-to-1. And so if I'm controlling this to theta 1 and that to theta 2 and that theta, and all of them are adjusting the velocities ever so slightly to get absolute thetas at the sacrifice of changing my theta dots, that means this will not be the same velocities that I would have because they're all going up and down, correct? But that net result may put me at some offset in the displacement. If I integrate these deltas, these differential positions, these small changes, then where I end up in that space may not be where I wanted to, because it was, yes, all of my angles are where they need to be, but I may no longer be where I'm supposed to be.
So if position is driven by velocities, we're minimizing positional error in real space.
So the position that we're really wanting is that position.
Right.
That we drive backward to this position.
By velocity.
This is the position we're interested in.
Got it.
Not these statements. But this position, if I control this position in my controller, that's going to drive these velocities.
Because the relationships aren't proportional.
Exactly. Because there's individual contributions from each one of those theta dots, resulting in dx, dy, dz, about x, about y, about z.
So mathematically, it still would be in those positions if we were to drive those minimal changes, but wouldn't be there in real space.
No, not quite. No. Mathematically speaking, because I don't have a 1-to-1 relationship through this Jacobian, because I've had these little changes over here, there's no guarantee that that's going to be where I want it to when I integrate this over time to position. So that means I can still do a position, but the position is driven by these theta velocities, not so much the thetas. So we can still do a PID position or a position controller, but we're driven from the error from these positions, not this space, even though this is what we command. Does that make sense? Now does it make sense?
I mean, I know what you're saying, but like, why? What is the significance of this? Like, why are you honing this into us?
Because when we think about controls, we think, I'm going to control theta dot, and I'm going to have an outer loop control my theta, right? But that's not really what I'm looking for. I'm looking for the position of the end effector. That's my control point.
Right.
My x, y, z roll pitch out.
So whatever theta values we plug in for that to derive the theta dots.
Doesn't guarantee
Yeah, are
that
relevant.
position.
Yeah, we want to. So
Because I'm sacrificing velocities to guarantee my theta.
you're explaining to us why it's necessary that we need to dictate the system's behavior from these variables.
Right. I don't want necessarily have the theta control be my dominant control variable.
So those thetas, when you change them, you're not gonna have it, let's say you wanna get to a certain point, right? So what I understand is
when you adjust those, you're not gonna get that exact point that you want.
Right, because as these guys are changing, right? So this is a velocity.
Right.
It's a velocity vector, that's a velocity vector, but they're two different spaces. And if I try to integrate this, does not mean I'm gonna integrate this at the same time, the same rate. Okay, because I've got the Jacobian in the way. Now the velocities make sense, but I'm driving this.
Okay, but then how would you try to get
So
that?
I gotta do, so that's when we come back
Inverse
to
Jacobian.
inverse Jacobian.
Yeah. So is this an argument for inverse kinematics?
It's getting us there, yeah.
Okay.
Okay.
It's also getting us to this guy right here. Okay, that's why we're talking about the inverse. So the inverse is really what we're looking for. That inverse Jacobian is back to the magic. That inverse Jacobian is telling us, so we can do the differentiation of our end effector. So we can go P, so we're going to define P to be our X, our Y, our Z,
0.
alpha, beta, gamma, for lack of a better bit. Okay. So that's my P. My P dot, so this is the end effector. This is global frame, potentially as well, right? So my P is also my end effector, and this is going to be our dx, our dy, our dz, about x rate, about y rate, and about z rate, my rotational rates, right? And so we want this right there. And so that's the idea of the Jacobian. We really have this, and so we need to find that guy right there. That's a set of velocities of each motor. Okay, so we can go from this guy to this guy and differentiate our positions from here, and we can go back and forth with this. But this right here does not guarantee the idea of the integration of our d theta. That's the point I'm trying to make. So we can go from our d theta to our d by way of our Jacobian. So Jacobian or our inverse Jacobian.
Okay.
But that
Now,
does
how
not
do we go from PEF to P dot? You drew arrows, but you didn't write the mechanism.
Oh, we can integrate differentiate.
Oh, okay.
So this is the integration and differentiation.
Okay.
So that's true in the end effector space. So this is our Cartesian space. But this guy right here, this is our joint space.
Okay.
But the caveat is I can't control these velocities. These velocities are described through the Jacobian and this guy.
So we're doing a change of coordinate system.
Yes, exactly what we're doing. The Jacobian does that coordinate system I don't want to say transform.
Translation. It's describing it.
Conversion.
Yeah, there we go. Yeah, it's converted.
We're converting from our joint space to our end effector space. That's what Jacobians do. So that's what's going on here. So we're actually going to do that one. That was the idea behind that statement that I didn't stress it quite as hard as I needed to. So that's why I wanted to go back to this one. You could be asking yourself a question, why do I care? Right? Why am I drilling this point? Because we saw that in the robot arm. But it's also true for a robot vehicle. So when I was at iHerb, and I was doing the control systems for that, they bought a controller from this company called Leomatic. And they had a 3-axis controller, and they were controlling velocities and they were controlling positions for like an industrial kind of mechanization, but for motion control. The problem is each axis was controlled to a theta, or to a displacement, at the cost of changing the theta dots. But the theta dots combine together to give you what's called our heading. So the differential velocity of the VL and the VR, when you change the velocities, you affect the heading value, the heading angle, which is the same thing we've got over here. This is kind of like the heading angle, right? And so those changes, well, you might have gotten VL or theta L and theta R, or displacement L and displacement R be what you needed it to be. To get those where they needed to be, you adjusted the velocities. And in the process of adjusting the velocities, you actually threw off your heading. And so you really weren't where you thought you were as you migrated or progressed from frame A to frame B, which is the same idea that we've got. Does that make sense? So they didn't understand that because they never had robotics. I had to educate them. I don't think they really still understood, but that's beside the point. All right, so let's see what else we were talking about. So then we went through when we did this little guy right here, which was pretty trivial, the implications for that. And then I'd asked you guys to look at the example 512. Then we looked at example 513, and we were given this Jacobian, where we had the inverse Jacobian, which was this guy right here. So we could find that D right here. And so this is the velocity in the end effector space. This is my joint velocity. So these are my motor rates. They have to move. So these are how fast my motors have to do in radians per second in order to achieve this velocity that was massive. And it was only an x dot, y dot, and z dot. Those are only 3 of them. I could have asked for about x, about y, and about z if we wanted to. If we did that, then our Jacobian would have to change to reflect those relationships.
It'd be 6 by 6?
No, it'd be 3 by 6 or 6 by 3, depending on how you look at it. Because this is still only 3. So there doesn't have to be a square matrix. Jacobians don't have to be square.
Oh, okay.
They're not orthonormal. Jacobians are not orthonormal. Wait. Okay. Discord. You guys love Discord, don't you?
Yeah.
Let's see, I need my. So, leads, you guys were supposed to talk to your team about the day for competition. Did you guys all talk to each other?
Not yet.
Not yet, okay. No. So, Monday, you guys owe me a date. Sound good? What date we're gonna do the competition? Team leads email me, yes. Okay. So, let's look at example 514, and then I think I'm just going to flip through the book instead of, I didn't do the slides for when I was looking at the slides. I just want to kind of highlight the book a little bit instead. So it'll work just as good. But let's go look at 514 first. So in this case, a hand frame TH is defined by and by the way, this hand frame, we now know how to compute those. That was exam 2. That TH that we did all the forward kinematics, you get to store TH, literally could be something that looks like this. So we could have a 0, 1, 0.
Like A1 times A2 times A3.
A1 times A2, A3, for all the way through could result in something that, it's never going to look this pretty, but it could be a 1, 0, 0, and with the position at 2, a 0, 0, minus 1, 8, and then this has to be a 0, 0, 0. Okay, that's T hand. Sometimes NuQ, I notice, uses that lower right corner. Typically, we've been using this one. Depends on the Craig. I'm more accustomed writing it this way, but I recognize that NuQ can change it up. A inverse J, Jacobian, is provided. So the J minus 1 is provided. The robot has a differential motion. So this is the end effector expression. And it's going to be moving in the x by 0.05, in the y by none, and in the z by minus 0.1. about x by 0, about y by 0.1, and about z by 0.03. And I wrote it out, so I'll just stick all transpose. So again, this is my dx, my dy, my dz, rotation about x, my delta rotation about y, and my delta rotation about z. And I probably should put that little squiggly thing on the top too. So those will go partial. And so the first question that's being asked is, find the joint space differential motions. So what are we looking for when I say joint space differential motions?
D theta.
D theta vector, or D theta matrix. So we're looking for D theta. It's going to be equal to our inverse Jacobian. You probably already knew that because I told you it's D. Times D. And if I gave you that, you could solve that by just plugging them in and saying that our d theta is going to equal to, our velocities are going to be equal to 0.05, 0.2, 0, 0.1, 0, and 0.08.
That's given, or you just calculate that?
That's what it's calculated. So if I gave you some inverse Jacobian, and I gave you this, we haven't gotten to that part yet. I gave you this part right here, and I said, okay, find the motor velocities, in other words. These are my theta dots. And by the way, your simulation is going to be doing this with the Jacobian or your robot arms. That'll be the next simulation that I'll post for you guys on Monday. Everybody with me so far?
What is that column matrix?
This is d theta. So this is theta dot 1, right? This is theta dot 2, theta dot 3,
Professor,
theta dot 4, and theta dot 5. Yeah.
where is the inverse Jacobian?
I just did write it down for you guys. I just said it's given.
It's given,
It's
okay.
given.
Oh, okay,
I
I'm
just didn't
confused.
write it down.
Yeah, I was like,
I didn't in the book, but I
Where
just
is
it?
it?
okay.
It was given. Okay, so here it is.
Gotcha.
It's been given. It's got so this inverse Jacobian is something here. Whatever.
And what is it? Could you guess like what the
You
dimensions are?
you can do the math right now and figure it out.
Oh yeah, sure.
Right?
So,
I just didn't do that.
So
okay.
wait, why did they give us the hand frame?
Because that's the end effective frame. That's what we went through. So here's my frame that's represented by my transforms that we did chapter 2 at A1 times A2 times A3. We found all those little transforms, right?
Mm-hmm.
What's that end frame state? All those together.
Okay.
Okay? That's what we're given for TH.
So
How did we use TH?
We haven't gotten to that part yet.
Oh, okay.
Yeah. So
that
the first question is, what are my thetas given my J minus 1?
Gotcha.
And given my D?
So now we have the thetas.
So now we know how fast our motors are turning.
is that theta dot or theta only theta?
These are theta dot. There's a little dot.
Oh, okay, theta dot. And the ones
So
right
this
here, theta
this
one.
is our joint space. Right, so this is our joint space. Tell me how fast each motor is turning in order for this velocities to be achieved. That tip's moving across something like this, as the hand may be rotating about the axis. Okay. Question B is saying, find the change in the hand frame. Given these velocities, and this is given, say, the start location, we've applied these velocities because we wanted the tip to move in this particular profile. So where is our hand going to end up, given this? for our next given, for the next given minute. So that's the idea here. So part 2 is B, is find the change in the hand frame. So we know our TH, right? But we need to find our delta TH. And this is why the H went down on the bottom, but if you want to put it up here, that's fine, I don't really care. Because it gets in the way with the D in front. So how do we do that? We need to find our delta operator matrix that achieves this.
Professor,
Yeah.
so start location is at the H, right?
What's that?
The start location is at the H. The start location
Yes,
is at the H.
it's at this guy right here, yeah. So this is
That
our
T vector.
starting location.
Okay.
And now we're going to turn the motors at this velocity.
Does it tell us for how long?
No, because we're just going to find the differential.
Oh, okay.
The differential amount. Exactly. So what we need to do is we need to find the delta matrix. So our delta matrix is going to be, again, we're going to have 0 minus delta z, delta y.
This was the thing that was similar to our S matrix, right?
This is our S matrix, in fact.
Oh, okay, okay.
This is our S matrix, which was actually derived from our R matrix,
Yeah. Mm-hmm.
which was actually our T matrix.
Well, the R came from. I mean, I guess. Okay, it's like take it out.
S came from R.
S came from R, and T came from R.
Yes. Exactly.
Yeah.
And then we also computed the D's as well. So that we have then our delta Z. That's a 0, and this is a minus delta X. That's a dy. We have the delta minus delta Y. This is delta X, 0, dz, and our bottom ones are zeros. And that's really by inspection, because that's what we have right here. That's our D. It gives us all those values, but we construct the delta operator from this. So we know that dt is equal to our delta th. So the new location from the small differential, t new, is nothing more than dt plus our t old.
Which is TH.
Exactly, so this is th. And delta t equals what? How do we find delta t?
Delta times TH.
What if I want to
Plus
find
TH?
it?
Is delta or dt?
No, DT equals delta times TH.
Okay.
So you can plug in for DT.
So that's to the, this is the new location. You say where. This guy equals this, right? So this is in Cartesian, or the
Global
the
coordinates.
UCS, let's just call it.
Universe. UCS.
So that's relative to the U frame. What if we wanted to find it to our end effector frame?
We have to do what you just showed us.
Exactly. So we could simply go back in, or we could kind of cheat a little bit. We could say our delta H is going to be equal to our TH inverse, our delta, and then we have our TH to, yeah, I'll call it that way.
Just TH, right?
Yeah, just TH.
Relative to 1 is that? Relative to 1?
And then remember he does the math trick where he moves that one in front.
And that would be relative to 1?
So this is going to be
Relative to hand.
Oh.
Remember the delta with the little T in the corner? That's what he's doing.
relative to our hand.
Is that,
So once we have our delta H right here, then we can find, we can apply our delta H to our TH, and that's gonna give us our delta T to our H frame.
Oh, do we need DT to the?
Yeah, so if I want to know then the velocity or the DT relative to the hand frame, then I could use that relationship instead.
Okay. And then, can you fill in the delta matrix? Like what we get the
It's the
value?
same exact format that we have right here. We could just perform this computation if we wanted to, or
No, I'm saying like, where do we get the values?
we don't need the values at some point. Technically, we have them because we computed it. We have this one already. Then we have the TH inverse times delta times TH. That'll give us our delta H.
if that would be the N effector?
That will be the differential motion relative to the end effector.
Oh, N effector, okay.
So this is the relative motion to the frame. This is going to be the absolute to the universal coordinate system. So this is relative to H.
So you can relate the differential motion by taking the inverse of.
Pre-multiplying by the inverse of the frame times that delta, and then you have the post-multiplied by the frame itself.
Professor, can you explain the stuff of the pattern?
Yeah, so that's what I'm talking about. So this is my delta operator, my differential motion relative to my H frame.
Mm-hmm.
This is relative to my UCS frame.
Uh-huh.
Okay. So I want to find that relative to my end effector frame. I can perform the T, take its inverse, times the delta, times our T.
Yeah, I get that. But those values at the bottom, what is?
Yeah, so for this guy right here, so this times our TH is going to equal to our delta T relative to our H frame.
And what is that last number?
That's just the error I was talking about.
Oh, okay, okay. Thank
So
you.
that's our DT. So that means we could find also our T nu, which we could if we want to the H frame, is going to equal our DT to the H plus our T to the H. So this is relative to H.
Okay. Oh, because we didn't have just a T.
Exactly.
We had T to the H.
So you can do it either way. So if you want to the universal coordinate system, you run the generalized delta. If you want to do it to the specific frame, then you would do it to this guy right here, where you have that frame right here.
Is that a W?
There is no W's. Where's W?
The H.
It's H. It's H. Yeah.
The one that.
I looked at W. Yeah.
Yeah, the problem is that the styluses aren't always appropriate.
Yeah. That's what I was confused.
So wait, hold on. I still don't know. Like, what do we plug into delta? Like, we can't just plug in variables.
We have delta.
Delta is
Delta's right
that.
here.
We get it from the D.
This is from D.
Yeah, no, I know. So we plug in all the values from D. Oh, okay. Okay.
That makes D.
Yeah, it has all of them.
That gives us a delta.
We had TH
Yeah,
as
it's
well.
just that
We
you
just
repeat
inverted
some of
it.
them though. You repeat. You make
So
some
we can
negative.
have a T as well, and I can make a T inverse from a T.
Okay.
Yeah.
Yeah.
So I now make a delta H.
Mm-hmm.
What if your T doesn't have an inverse? Oh, it has to by definition.
No,
Right.
yeah.
Yeah, that's right.
T has to have
Yeah,
an
it can't mess
Because
up.
it was already processed.
Yeah, yeah. All right, that's perfect. It's
So
foolproof.
that all makes sense?
Yeah.
Or you could do it the long way, when we did it back over here, where we went through and found the cross product of everything that we did right here, and that's the other way of doing it.
I like this one.
The other thing is, here's the other thing, is I can do that, and then by inspection, I can extract this particular vector of velocity. Because it's exactly from this guy here. Right here. This is by observation. I can find exactly what my relative values are right here.
So we just need to make a Python script that does that, and then feeds it to our motors. It's pretty easy.
And so that's actually what your next computer science can do.
Yeah, well, that's not too bad.
And at any point in time, you have a Jacobian. And Jacobian, those values are constantly changing because they're dependent upon the theta combinations of all of the joints. Remember, it's partial to one, partial to the other, right? In fact, if we go back to our Jacobian matrix intro, let's just go back to it real quick. Right here's our Jacobian. Right, here's our partial for all of F1, right? F1 relative to X1. So this is my joints in the bottom. These are all the combinations of each one. We did this guy right here. Whoops. No, I'm not going to say it, obviously. And I think this is the guy we were talking about right here. And let's see, where was it? There was a slide that I did for you guys. Oh, here it is, yeah. Yeah, so this is our Jacobian function, right? So here's our d theta 1,
Right.
and this is the functions of theta 1 and theta 2, which is the derivative, right? It's a partial derivative with respect to each one of these guys relative to how you construct each one of these things, an x, a dx, and a dy. Go back to here, you can also see. Starts to make sense now? So at any point in time, because these thetas are changing, this Jacobian is changing, constant. It's not a constant matrix. Like the transforms were constant. We go from here to here, it's constant, right? Jacobians are not constant. What is constant is the expressions that compute the Jacobians.
They did.
No, these guys, so the expression, L1 sine theta 1 minus L2 sine theta 1 plus theta 2, that expression is constant. But these thetas are constantly changing as you integrate this over time.
Mm-hmm.
And therein lies why these can change. Does that start to make sense on that conversation we had earlier? When you guys have the homework, it'll help you guys, trust me. And then I'll give you guys the computer assignment. And I haven't written it because I'm not exactly sure what I want to have in it. That's why I haven't done it. But let's go look at, before we move on, does this make sense now? It's starting to make sense. It's starting to click, right? So let's go, let me just do this one. Any questions? I don't know how many faculty actually go through this amount of detail. Clint?
My phone.
Okay, so here we are. Let's pull up Copelia. What I think I'll do for Monday, I said I was going to do this on Monday, but I just didn't have time to make the example. So I'll make the example in Copelia and show you guys the planar robot and have it move the Jacobians, and you can see how the Jacobians are behaving as we do the computation. So if we open up, we can do the IK you want, just because we can control where it goes. And this is where we turn on display the IK, or the Jacobians. So they're constant. These are changing ever so slightly because
No, it's not moving.
it's moving, but it is intentional. This is actually probably some numerical integration error, more than likely. So there's some stability integration as it's performing a constant integration. So we see kind of flickering around there a little bit. But again, if we move our destination dummy, it tries to move it along X and Z. And we see those values from the Jacobian changing. Like I said, I think I'll go ahead and make a planar robot arm for you guys. And then we'll maybe do a 2 or 3 joint arm. And then we'll take the Jacobian that we saw right there, the very simple plan. Because, I mean, all it is a twist. We saw how it works, but we'll put the planar one together because I think it's easier. Where we can say, look, this is where it's at. And my Jacobian theta happens to be, theta 1 happens to be this, theta 2 is this, and theta 3 is that. And we'll see when we perform that Jacobian that that's exactly why we're getting these relationships, these values, to see it for real. And if we look at it, here's my X, my Y, my Z, this is my global reference frame. So this is when integrating these velocities, these joint velocities. So I think what I'll do is I'll print the joint velocities too. We'll integrate those joint velocities to get to our position. And we'll see X dot Y dot Z dot about X about Y dot Z dot, so our delta X, Y, Z. And then we'll construct that little vector for you guys. And we'll see it, and I'll go ahead and print it out so you can see that in a one-to-one. I think that'll help you guys a lot. Yes? But as you saw how the Jacobian, that Jacobian is a function of that theta, not theta dot, but of that theta. That's what's giving us our inverse kinematics. Remember when we looked at the inverse kinematics papers? That's how we're computing the inverse position. So it kind of goes back and forth. And it all references really around Jacobians, which is why I'm stressing them when I am. So inverse kinematics isn't magic, but when you have a lot of examples or a lot of solutions, then it picks the best solution, typically from an LMS. But we went through the weights and talked about the three approaches that were typically done, as it's trying to find the optimal from the set of a whole bunch of solutions. But if we're in a 3x3 or a 3-joint planar, it's pretty fixed. There's not a lot of solutions. Okay, David, you had asked a question on the script, I think, right? Yeah, so let me see if we just pull the script up. No, that's the pink spray.
Yeah, what is that? Yeah, IK.
Yeah, IK.
Yeah, there you go.
Yeah, so this was started with the.
Scroll up real quick. What?
I started with the tool to auto generate, and then I modified it. So what you do is you pick the tip, the dummy to the base. So you pick this last joint from here down to here, and then you tell it to find the inverse kinematics. So go through the modules, and it's under kinematics, and then we do the inverse kinematics generator. So that's how it generates the scripts, and then you modify it from there. I thought I also had. I'll find out where it went. I thought I had one that also was showing the loads on each one, the torque.
Question: What is that self variable do? Self, yeah.
It's just so it's referencing self in this kinematics.
So assigning the value, no?
Yeah, what the heck is dot?
Yeah, it's the dot. It's the parent.
Oh, is that just floor?
No, it's the parent to the object.
Oh, okay.
That's what the dot means. So it's kind of like through the IK right here. This is the group where you're putting everything together. But remember, it goes from back to one-to-one, going back to one, back to one, back to one. So it changes it all the way back for each one. Then here's the graphs. Oh, there's the graphs. I just didn't have it running. That's right. So then here's all the graphs that we have right here.
You're gonna upload this, right? Or?
I thought it was uploaded.
It's already up. I'll just look
Isn't
at
it?
canvas.
No?
I don't know. I didn't look.
Okay. I will upload this tomorrow. Please feel free to email me if I don't. Or put me on Teams. I got a million things. I keep saying that. The problem is you guys are better at reminding me honestly than I am. So remind me. But here's what I want you guys to see. So this is kind of cool actually. Close that down.
Wait, go back. Let me see that move the J1 joint. Did you have that same issue I ran into where it was? Or like, were you manually moving? Wait. Well, go back to it. There's like a comment. It says it's like right above the graphs. It's like move the J1 joint.
No, it's just moving J1 joint. That's all.
Oh, like automatically, like that's when it does. Okay.
And then a lot of this is stuff are auto-generated, but like the graphs are not auto-generated. I added those in. What's kind of cool, and this is what I wanted to show the graphs, is as it's running, put the Jacobian over here, let's pick the tip, and well, like I said, I think it'll make more sense when we see this in the planar robot instead of the, I have to make a planar robot. I may make do a 2 joint, and you may have the assignment for a 3 joint. So watch this. So I'm going to move the dummy. And notice the velocities are changing, right? Notice not all of them are changing, but a lot of them are. So you can begin to see this guy right here and how it reflects the position. Let me move velocity over this guy. In fact, I don't want to care about torque right now, so let's just cover up torque. So watch the velocities. They're going to go. And right now they're just maxed, right? They're just at a certain rate. They're not going up and down. They're just at a constant. So there's been no acceleration, so it's never turning on, which is not necessarily good. Here we can see the position reflection, and we can see these guys right here. So again, this is for joint 1, joint 2, joint 3, 4, 5, and 6.
Is there a way to like make the IK that's running within Coppelia like export variables out to Python in a different IDE?
Anything in here in that script can be externally addressed or accessed.
Okay.
Which means you can actually do the entire IK external to Coppelia.
No, I know that. But I was saying like because I want to export all the velocities that it's calculating right now.
Oh yeah, just export it out.
Yeah. Okay.
Yeah. So I'll send you the code that I had for the robot, the ground vehicle. But yeah, you're just getting to sim.get joint velocity.
Oh, and it'll just give it to you.
Yeah.
Oh, that's perfect.
Obviously, this number got real small because there's just noise. Now, here's the other thing. On top of this is going to be my lead into Lagrange. These are my torques. Now, watch my torques as I'm moving. I know this is probably too big. Let's just do it like that.
They're like impulses or?
So there you see, we see that red one?
Okay, yeah.
And then we have it go down here, right? So joint 2. So this is joint 2. So that's where a lot of torque is because it's moving all of this, right? And we can actually see it's not necessarily linear. So the question is, if we exceed that torque, or if we try to move it too fast, I rate limited how fast this can move. It's rate limited by the code base. In fact, if we look at the code base real quick. In fact, you can even see the position I printed them all out. I go back to, oh, by the way, there's one thing I need to show you guys. When we're doing inverse kinematics in the arm, let's go ahead and look at the joints. We look at the dynamic properties of it. We need to be positioned right here. So we have to have these guys right here set up that way. But then if we look at the IK, we put it into a different mode. Let me see if I can find out where that's at.
Put it into kinematic mode, right?
Exactly.
Yeah.
So here we are, we set the mode for the joint to be kinematic. It needs to be passive mode.
Mm-hmm.
So when we're doing this, that joint group, we need to make sure it has that passive mode. It does this for you from the automatic script, but I wanted you guys to be aware. You can still do everything. You can still set the commands to move, but we're really kind of doesn't make any sense. So in the code, it puts it into that inverse kinematic mode, right? Right here. Actually, right here.
Joint mode passive.
Set mode.
Can I see the joint settings?
Oh, back to where it was?
No, not dynamic. No. That's not a joint.
You want to see the joints in the dynamics engine?
Before the dynamics, just. Oh, so you have it in dynamic mode.
Yes, it's in dynamic mode.
I converted all of mine to kinematic mode because I couldn't get the IK to work. It was being dumb.
That's why you have to set it here. So if you don't set it here, you have to set it here in code. So you have to put it in.
Do my joints need to be in dynamic mode?
Hmm?
Do my joints have to be in dynamic mode?
For IK?
No, just in general. Like, do you want it in dynamic mode?
You can do it either one.
Oh, so kinematic mode's fine?
Should
Okay.
be. In fact, if we look at this guy right here. This was the code for that, and those modes are set to dynamic. Controlling position now.
Yeah.
For the robot vehicle, I'll give you guys the Copelia sim file for that as well, just so you have that, so you can see how we use velocity versus positions.
Do you have any prismatic joint examples?
Yeah, this has a prismatic in it.
It does. Yeah. Can I see it, like, go to the prismatic joint settings? How do you, like,
So I have two of them, and they go inward and outward opposite to one another.
how did you limit their motion?
Max velocity, you mean?
Maybe?
Target?
You mean the motion?
Oh, right there, configuration at the top, yeah. Yeah, how do you figure out your distances?
That's physical. That's how big it's going to go. That's how big that it can move inward and outward in meters.
Mhm.
It can only go up to minus 0.025. So this is my minimum. This is my maximum.
Okay.
Yeah, you just have to play with it based on the geometry you're on.
Yeah.
Are you moving both meshes away from each other or just
So
one?
simultaneously, yeah. And by the way, the prismatics, the Mujoko is probably the better engine to use.
Yeah.
Otherwise, they'll tend to fly apart.
Mhm.
ODE and Bullet don't tend to do well on the linear displacements. But you can see there's just the prismatics moving backwards. So it's sitting right here, we can go all the way out here, but this is the base. That's my 0 point. You can go inward, my minus 0.25, but I can go outward by twice that.
Gotcha.
And then this is the same, but opposite. But I rotated the thing around such why it's still minus 0.025.
Mirrored it.
And if you guys want to see the code for that, because it does open and close, there they are right there.
Oh, you just set the position.
Actually, here's the velocity. Yes, the position. That's right, position.
Okay. All right.
Okay, does it help you guys?
Yeah.
John's not convinced. Again, I think Monday we'll go through, I'll make the planar example for the Jacobians. And just like we saw, just like we see, like when I run this one, close this one off, close this one off. And we see this, and we see, whoops. Here's all the parameters for torque, velocity, and position. It's really being graphed right here at the same time. But you can see that. And then I'll try to graph it where you can see the quaternions or the rotations as well for theta angles. Exemplify everything we did. And I'll probably throw it in an example that we did, and we see it in Copelia. I think that'll help you guys a lot too, yeah?
Okay.
Makes sense? Because that will be basically what you're doing, you'll extend that into your simulation.
Hopefully we'll get everything done in time.
You will. Okay, so the last thing we're gonna talk about, we're wrapping up. The Lagrange, I got 7 minutes real quick, and I'm gonna use this to explain what's going on with the Lagrange. So if let's see did I rate limit these motors? Let's take a look real quick. Let's go ahead, let's see, joint 2 tends to be, joint 2, that's the one that's doing a lot of the heavy lifting. If I'm moving that planar spot. So if we come over here, and I gave it a max velocity of 2.5 degrees per second, with a max torque of 2.5 newton. Let's suppose we want to make this go faster. Let's make it 10. Okay. In fact, let's just keep that there for now. I don't know what's going to happen, but we'll see how it goes. Let's see if that hurts us or helps us. Should move much faster. Get to my dummies.
Well, wrong thing. Oops.
So it goes a lot faster, right? Because I changed that velocity limit. So now I can go
Zooms.
a lot faster. It does. And so we see that position changing, and I can see it still maxes out on that particular joint. So joint 2 is red. So it's going plus minus 2. See, the other ones were 2.5. That's they're 2.5. It's almost an instantaneous acceleration. You can't see it, but it's got pretty good acceleration, right? If I change it to be really slow, then I could see the accelerations. So the question is, I can control the velocity, but do I go to velocity instantaneously? No. I have a torque that I have to go to, right? So I have to accelerate. So acceleration is force. My mass is constant. If I assume a constant mass or a full extension, then I say that the acceleration is what's going to change. So if I accelerate slower versus faster, which is going to require more torque? Fast acceleration is more torque, or slow acceleration is more torque? Slow. Right. Fast. Hey, what do you know? Why?
Greater change of energy.
It rotates faster.
You're on the right track, but that's Lagrange. We haven't talked about Lagrange.
Torque is a function of force times lever arm.
Right. It's the function of force, and as the mass is constant, it's related to acceleration, right?
Yeah.
Higher acceleration, higher torque. What is torque proportional to?
RPM?
Current.
Oh, current.
So if I current limit, am I going too fast? Am I accelerating too fast?
No.
Yes.
I thought you current limited.
If I'm current limiting, if I hit the current limit, am I accelerating too fast?
Oh, yeah.
So in other words, I'm asking for 10 amps because I want to go that fast because it takes that much torque, but I can only give 5 amps. Which means I'm trying to accelerate too fast. Or I have too much load, or a combination of the two. So the amount of force I have to look at is, I have to be very careful how much force I have before I figure out how fast I can accelerate. All right? That's what we talk about in Lagrange. So we're going to jump in real quick into Lagrange. I'm just going to read it from the slides here real quick instead of write everything out. I don't think I have. I haven't uploaded yet. But let's just go talk about it anyway. I'll give you a quick intro. Let's see, what is this? Jacobian IK. It's Lagrange. I have no idea what that is. Okay, so what we're going to talk about is we're traditionally thinking about, and that says motor theory. That's even funnier. Let's just go to These are labeled very oddly. But if I go by date, that's probably the best thing to do. Okay, that's
Brushless.
even funnier. That's
Brushless motor.
just flat out into a different topic. Oh boy, but we went over all these, didn't we?
Yeah.
Yeah, we went through all of these things. Obviously, I was having fun naming them that day.
That one.
That's probably the one we want, right?
Yes.
Yes, there we go. So the idea behind, that still says motor steering, but that's so what. The idea, let's just see what the other one was. Intro background.
Probably that one, actually.
Motor theory.
Motor steering.
Still.
Okay. So the idea of Lagrange, and I only have 3 minutes, so it's going to be very brief. So I'm just going to give you a quick overview. The idea behind using Lagrange is instead of using F equals MA everywhere, which can get quite cumbersome, especially when you have 6 joints, we use Lagrange. And so the idea of Lagrange is really, it's pairing kinematic versus potential energies against one another. And how those energies are split up through a function of motion, which is why we covered differential motion first. So we think about what we've done. We said, okay, look, potential energy, kinematic energy, as a function of motion. Motion is described as differential motion. So what did we just get done talking about? Differential motion. How the D vector relates to the joint vector, or the joint space. So if I want that to move very fast, that we saw in Coppelia, right here, we want to move very fast, we're going to see high torques invoked or imposed upon that particular guy. In fact, we could see it right here in joint 2, right? That was really taking the bulk of the work. And if I try to change it back and forth, I'm really spiking it. Ignore these guys right here, because that's really nothing more than a point of inflection error. That's this guy right here, that little spike. It's caused by the change in direction, because this is a non-smooth surface the way it's computed. So if we did make it smoother, instead of doing something like this, right, having it jerk, if it was nice and smooth, do you think it would take more energy or less energy? Or should I say more current or less current if it's smooth?
Less,
Why?
because your differential step is smaller. Because you're taking smaller steps.
So when we understand that the energy from a potential energy to kinetic energy is a function of the motion, the differential motion, the velocities for the joints and the arms. I mean, you can speak to joints and arms the same way, because we now know that the joints and the arm is really nothing more than the relationship through the Jacobian. Right? We've just gone through talking about for the last few weeks. So this differential motion can drive the Lagrange, and we can use that differential motion to describe the energies from one state, and the state that we talk about is an energy state, from one state to another state. And we can look at the velocities and the partial velocities of one to the other in order to construct that relationship. We're still just looking at velocities. And from there, we can differentiate from our position to get to our velocities. That gives us our Lagrange. We can use that technique by using this guy right here, using the differences in the energy to construct these parameters, L is the Lagrange, from the potential energy, the kinematic energy, or the kinetic energy minus the potential energy. And we'll go through, then we're going to get this guy right here. So we have the partial with respect to a variable times, and take a partial with respect to t to find the kinetic energy, and then we can also find the potential energy. So we now know how to do that. And so the idea is we'll actually be able to do the k component, we can find the p component, from there we can find the L, and we'll see that we can do something right here. And so here's our theta dot 1, here's theta dot 2, theta dot 1, 2, force of 2 degrees. So we're going to go through this in detail. Everything is going to be watch and listen. I'm not going to make you write this because we're going to go through this relatively fast. Okay, because at the end of the day, we're going to get something like this.
There's so many J's and I's.
On that note, I'm going to leave you guys to have that. I will post these slides, Lagrange, to the directory. I will post the arm